Okay, Physics 20s, welcome to our last chapter of the course. We're moving on to chapter 8, and we're going to be talking about waves. How are you seeing and hearing me? Now, I know it's through your device and through the internet, but let's think about what's actually going on here. First of all, this is not a live representation of what's happening. This was recorded yesterday or maybe a long time ago, depending on when you're watching this lesson. And how this information is coming to you is actually quite incredible. So first, this gets recorded by a camera right here, which is on my phone, and that's able to detect light. Now, light is a wave that is moving at 3.0 times 10 to the 8 meters per second, really fast. And it comes from that light. It's white light. It's going to bounce off my face. Some of it's going to get absorbed, some of it's going to get reflected, and then it's going to go into that camera. Now, the camera has a sensor that's able to pick up that information and store it. But also when I'm speaking into the camera, there's going to be compressions and rarefactions of the air caused by my voice that's going to compress and separate out the air into waves like this. Now the camera is also able to pick that up and store that as information. Then that's able to be stored onto YouTube. You open it up on your device and you click, and then boom, there's the video right there. But then your device has the ability to turn on lights in a series of ways that matches the light that was recorded, and it sends these wavelengths of light out, and then it also shakes back and forth with a speaker to make the exact same compressions and rarefactions to duplicate the sound. And they're matched up with timing as well, so that when you see these wavelengths of radiation hit your eye and these shaking back and forth air particles, you are able to interpret that as me talking to you through a screen. That's actually pretty mind-blowing when you think about it. And all that information is being able to be transferred by waves, and that's what we're going to be studying in this section. We're going to talk about more sound waves and mechanical waves in Physics 20, and there'll be more looking at light waves and EMR in Physics 30. So here we go, let's look at waves. So first we're going to look at 8.1. This is going to be an introduction to waves, go over some basic properties and kind of what waves are. The first part we're going to look at is wave types, and the first one is called a mechanical wave. A mechanical wave requires a medium or requires some amount of matter for it to be transmitted. So sound is an example of this, and it gets transmitted through the air particles, shaking them back and forth. Water waves is another example of this, waves through a spring or a string or anything like that are all mechanical waves. Ones that don't require a medium are called electromagnetic waves, and this is what light would be considered. Now this diagram we're not going to be looking at in Physics 20, but it does show what a EMR or electromagnetic wave is. And this is a wave in a field. It's kind of hard to think about that, kind of like a gravitational field. There's going to be fluctuations in it. This is a wave in an electric and magnetic field, and they're perpendicular to each other. So you can see this red one, which is the electric field going up and down like this. That's in this plane on that graph. And then the blue one is supposed to be on this plane, kind of going in and out of the page. So the blue comes out of the page, into the page, out of the page, into the page, and they're supposed to be at like 90 degrees to each other. But again, that's a look at Physics 30, but there's some interesting stuff you're gonna see there. The next two types of waves that we're gonna look at is longitudinal waves and transverse waves. Longitudinal waves are where the particles are moving parallel to the energy. So they kind of look like this. We can see some lines spread out, close together, spread out again, and then close together. So the movement of the particles in this wave, say this was like, is a good example of sound, they're moving back and forth in this direction, and the energy of the wave is moving in this direction. So they move back and forth this way to cause compressions, which we can see here. Compress. And then when they spread out in places like this, this is called a rarefaction in a place like that. So moving back and forth this way, energy being transmitted this way as well. So this would be like the source of the wave, and this would be where we like hear it. So say we have an ear listening to it at that point, parallel to the energy. The next one is transverse, where this is going to be going perpendicular to the energy. So here we have a particle, say right here, and right here, and right here, and they're going to be moving up and down in these directions here to cause the wave to transmit energy that way. My best way I think to think about this is if you've been to a arena where they do the wave at a sporting event, the people all stand up and down like this. They're moving in the vertical direction, but the wave goes around the arena in the horizontal direction. So I think that's a good way to think of it there. Now we're gonna look at the parts of the wave, but before we do, as this animation kind of shows how it's drawn, I think it's important to look at how it's moving. We can see that as it draws this, it's gonna keep repeating it. It spends most time up here at the top parts, and it's moving fastest right here in the middle. And this should be really familiar to simple harmonic motion. And you can kind of imagine that this would be similar to like a horizontal spring moving up and down if the whole spring was also moving along this way. It's going slow and actually stops right at the very top there, and it's going fastest at its equilibrium point. And this, I think, kind of shows how waves and simple harmonic motion are connected. I'm going to try and show this as well with this circle here. It's just going to try and track the wave up and down as the wave moves through, and we can see that it looks like the ball is going to be moving in simple harmonic motion. Now the animation isn't perfect, but you can see it kind of follows it like that, like the ball was on a spring and it was moving up and down. And that's actually how you can generate a mechanical transverse wave as well. Say this blue line here was a spring or a string, and you're holding on at this gray circle. If you move your arm up and down in simple harmonic motion, or even better, if you attach it to a spring, like attached to the roof, and it's going up and down in simple harmonic motion, the string will make this transverse wave if it's connected to something on the other side. So that kind of shows how they're related. And I want to show that because when we're looking at the parts of the wave, we put this line here to show equilibrium, and we measure the amplitude of the wave, really similar to how we did for simple harmonic motion, the distance that it's going to be going above and below the equilibrium point. The other part I want to put on here is we call the very highest points peaks and the lowest points troughs. So if it's going through a peak or a trough. And usually we just use those in reference to what direction the waves are moving. So if there was a particle right here, it's already at its highest point, it's going to start moving down next. And if there was a particle right here at its lowest point in a trough, it's going to start moving up next, as it's going to be going up and down like this the whole time. Also, it's for measuring how far one wavelength is. This is how we measure how long waves are, and it's really similar to a cycle. It has to go through the whole motion of that kind of simple harmonic motion, the top, the bottom, back to the top. That was a cycle. The wavelength is going through the whole motion of the wave. So we can measure this from being from a peak to peak. It starts at the highest point, goes through the whole bottom, and back to the top. But similar to a simple harmonic motion, you can measure it anywhere as long as it's gone through the full motion. So we could also measure it from here. It starts at equilibrium, goes through the lower part, upper part, and then back to equilibrium again. And it will be the exact same length the whole way through the wave. So even if we measured some peaks over to this side, they should still be the same distance apart as the other peaks were, and that'll be consistent throughout the whole wave. The other parts of a wave that are kind of hard to put on that diagram are velocity and frequency, and they're related to wavelength in the equation we're going to see on this slide. So first it says that wavelength is the length of one full cycle. We saw that on the last slide, from a peak to peak, a trough to trough, equilibrium, up and down, back to equilibrium, as long as it goes through a full cycle. The velocity of a mechanical wave is determined by the medium. So it's saying how fast that wave is going to be moving. So if we have one like this, again, it's going to be moving in that direction. So you shake a string and the wave goes across, how fast it's going to move is determined by whatever you're shaking. If it's like a really tight spring, it's going to go fast. If it's like a really loose string, it's going to go slow. So that's determined by the medium. Now, before I get to the last point, I'm going to write this equation. It's our velocity is equal to this symbol. It's called lambda. It means wavelength. I'm going to put that in here. Wavelength multiplied by the frequency. I'll put that maybe just to show hertz, so we remember that it is frequency. Now this is given to you on your data sheet. It's not too complex a formula because there's no squares or cubes or square roots or anything like that. It's pretty simple, but we need to know the relation between these things. So that's what it says here. It says if you're, say, shaking a spring, spring is attached to the wall, you're shaking it up and down and making waves on it, and you pull it tighter, that's going to change the medium, so it's going to change the velocity of how fast the wave is going. It says if the velocity changes, the wavelength is also going to change and the frequency doesn't. So just to kind of draw this out, say we have this spring like this, and your hand is over here, and you're shaking it up and down, kind of a weird looking hand, but you're shaking it up and down. That's gonna be making a wave go like this through to the other side. Let's just say that it's attached to a wall over here. Said if we pull that tighter and we're shaking it up and down, say once every second, that's gonna be our frequency, 1 cycle per second. Just because I pulled it tighter doesn't mean that I can go up and down in 1 second and the wave's gonna hit the other side in half a second. We can't change that timing. That has to stay consistent. So the frequency is gonna stay the same. Kind of things like the frequency that the wave's gonna be hitting the wall. No matter how tight the spring is, how fast I'm moving my hand has to be equal to how fast it's hitting the wall. You can't kind of change time there. That's the only relationship I kind of put in the notes here, but there's some other good relationships I think to look at. Let's say we take another spring, and this time we're not going to change the velocity because that's actually not too common that we're going to be changing the velocity of this spring. But we could change how our hand's moving. So say here's our hand again, shaking the spring up and down. And first we're shaking it really slowly. This would be at a low frequency. We're gonna say the spring's staying the same. So I'm gonna write velocity is equal to lambda frequency. And as long as we're not changing the spring, velocity is gonna stay the same because that is determined by the medium. Okay, so just using an easy number, say it's moving down the spring at 1 meter per second, 1.0 meters per second. When I shake it, that's how fast the wave moves down the spring. If I'm moving my hand really slow, so with a low frequency, the wavelength is going to be pretty high. By the time I take up to go down, that's gonna make a really long wave, all right? Now, if I'm gonna change that, I'll just scratch these out. If I start to increase the frequency, so now I start moving my hand really fast back and forth, the waves can't go any faster through the spring. So now there's gonna be a lot of waves on that spring. To get them to fit in there, they're gonna have to be closer together. So the wavelength is gonna have to decrease. I know it's kind of hard to show without actually shaking a spring. If it doesn't really make sense for what's happening in real life, we can just kind of look at the math. For this number of velocity to stay the same, which it has to because it's determined by the medium, if we're going to increase this number has to go down. Think of it as like velocity is, I'm gonna use just another easy number. Let's go with 10. So imagine I erase that decimal. 10 meters per second is equal to our lambda times our frequency, 2 numbers. Say we had before it was 2 for our wavelength and 5 for our frequency. That would make sense, 2 times 5. If we're gonna increase our frequency here, let's say to 10, our velocity still has to stay at 10. So what does that other number have to be? It has to be a 1. So by this number increasing, this number has to decrease. And that's really the relationship that we're looking for. Same for the opposite one. If I decrease my frequency, I have to increase my wavelength, okay? So that relationship comes up quite a bit, sometimes in some questions. This one does too. If it's changing medium, it's just a little bit less frequent to do, I think, for some of the questions, but definitely still could get asked about it. So make sure we know both of those relationships. But now we're just gonna do one example using that equation. So it says a sound wave has a frequency of 540 hertz, and that might seem high, but before we were just looking at something oscillating on a spring or a pendulum. For sound, it's gonna be really high. So 540 hertz, if the sound is traveling at 340 meters per second, which is about the speed of sound, what is the wavelength of the wave? Okay, so we have our wave here, whether it's electromagnetic or mechanical. We're still gonna describe it with V is equal to lambda F. Again, that means wavelength times frequency. This one is asking for our wavelength. So to rearrange, all we have to do is divide by frequency on both sides. It's pretty easy to do that. The velocity is 340 meters per second, and we divide by the frequency of 540 hertz. And we should get an answer of 0.629. Let's just go back and check the units because it's always good to make sure that those are working out. We have meters per second divided by hertz. Hertz is the same as cycles per second, okay? So now we have this meters per second per cycle per second, which is a little bit hard to kind of go through the math here. I know some math teachers kind of look at kind of the big division, and then we have like meters, seconds, and then cycles, and then seconds. And they say that you can like cross the two bottoms out. I'm gonna look at it a bit different by timesing by the inverse. Some math teachers do that as well. Maybe I'll just show both here. So meters per second divided by cycles per second would be the same as meters per second times by seconds per cycle. So either way there is fine, but you can cross out the seconds that way because they're both in the denominator there, or here we have it in the top and bottom, they cancel out, and either way we get meters per cycle, meters per cycle. And our cycle is one wavelength. So how long is the wavelength? It's going to be 0.629 meters. So the units do work out. And let's just round that to 2 significant digits. Oh, actually we had 3 significant digits, so we can leave it like that, 0.629 meters. Okay, so that was just an introduction to looking at waves. A lot of this chapter is going to be theory based. I think the second half of it's more calculation, but for the first 3 lessons, there's going to be a fair amount of theory in that. So make sure you ask lots of questions, and it's kind of harder for me to tell if these explanations are making sense through videos. So send me emails, join the meets if you'd like, and I will see you in the next lesson.